Hi everyone, welcome back. Today we'll get into section 4.1 on the first derivative and graphs. So remembering that the derivative is really describing a rate of change. Sorry about that. There we go. Okay, now that I'm off the cord, the first derivative describes a rate of change of a function. So when a derivative is positive, the rate of change is positive. In other words, the function is going up. Similarly, if the first derivative is negative, f is decreasing. So we'll start with one that should be familiar from your Math 165 days and your Math 100 days for that matter. So we'll do f of x is x minus 4 quantity squared plus 3. So you should recognize this as a parabola shifted to the right 4 units and up 3 units. We're more interested in what can the first derivative tell us about this graph. Well, if we want to differentiate, I would go ahead and FOIL this out and turn it into an easier to use format. So x squared minus 8x plus 16 plus 3, or just f of x is x squared minus 8x plus 19. So our first derivative, f prime of x, 2x minus 8. And since I'm looking for places where the derivative is positive, negative, or 0, we'll start with the 0. We'll just use a let line. Let the derivative equal 0. So solving that, x is equal to 4. So if the derivative is 0 there, we have a horizontal tangent line at x equals 4. If I want to know where the graph is increasing or decreasing, I basically just make a little number line. So we know what's happening at 4, and then I just use test points. So I can maybe test x equals 0 and x equals, 5. So f prime of 0 is a negative. Happens to be negative 8. All I care about is that it's a negative. And f prime of 5, 2 by 5 is 10. 10 minus 8 is a positive 2. So first derivative is negative on this entire interval, so that means f is decreasing. Negative infinity, negative 4, open interval, or open interval for that one. The tangent line is horizontal at 4. Similarly, for our next interval, the derivative was positive on that interval, so f is increasing on that interval. Apologies, that should have been a positive 4. 4 to infinity. And that does fit with what you know about the graph. A is positive, so it's a parabola that's opening up. Based on this first version that I showed you, where it's sort of easy to eyeball the shifting happening. It's parabola opening up. It's in quadrant 1, vertex at 4, 3. So horizontal tangent line at the vertex. It's opening up, so on the left side, the function is coming down, it hits 4, 3, turns back around, then the function is increasing after that. All right, so critical numbers are numbers where either we have a derivative of 0, which we just worked with. There are also places where the derivative does not exist. So, two ways to find those. F prime of x is 0, or f prime of x does not exist. All right, so next one we'll look at, f of x is x cubed minus 4. This one we can dive right into the derivative. There's no work to do in simplifying. So f prime of x, 3x squared. And again, we let the derivative equal 0. So x equals 0 is the only solution to that equation. So we don't have anywhere where the first derivative does not exist. The first derivative was just a plain polynomial. Those are defined on negative infinity, infinity. So we'll test out maybe x is -1 and x is +1. Again, if I'm interested in increasing or decreasing, I'm interested in the derivative, not the original. So we're plugging them into f prime, not into f. So f prime of -1 is +3. F prime of +1, also a +3. So f is increasing, negative infinity up to 0, also on 0, infinity. So this one, we have a vertical tangent line. Or no, my apologies. Next one has the vertical tangent line. This guy has a horizontal tangent line still. All right. So our next one, we'll switch up, we'll call it g of x. We'll do -2 by x plus 3 quantity raised to the 1/3. So a cube root function. A is less than 0, so it is a flipped cube root function. Okay, so g prime of x, we're already in the right format. So this one we're using our chain rule. So hang on to the -2. Exponent becomes a coefficient. And your x plus 3, drop the exponent by 1. And multiply by the derivative of x plus 3, which in this case is just a 1. So g prime of x is -2 over 3 times the cube root of x plus 3 quantity squared. Okay, so first things first, since this is our derivative, if we try to let this thing equal 0, as soon as I try to solve that thing by clearing the fractions, notice we get the false statement that just 0 equals 2. There's nowhere that our first derivative is 0. So if you think just cross multiplying, 0 times anything is 0, 0, you can think of as 0 over 1, we get 0 equals 2, which is false. So we have no horizontal tangent line. But we do have a place where the first derivative would be undefined, and that's at x equals -3. -3 plus 3 is 0, 0 squared is 0, cube root of 0 is still 0, 3 times 0 is still 0. Negative 2 divided by 0, undefined. So we are undefined at x equals negative 3. So that means we have a vertical tangent line at x equals negative 3. So next we'll see where we're increasing, decreasing, or constant. So we just break up the number line again. This time our critical number is a negative 3. So we'll test out maybe x equals negative 5 and x equals, I don't know, 0. So just one per interval. So trying that out, again in the derivative, so g prime of negative 5, negative 2 over 3 by the cube root of, let's see, negative 2 quantity squared is 4. So negative or positive is a negative. So we're decreasing on this interval. G prime of 0, negative 2 over 3 times the cube root of, sorry, it's my little cat there. Cube root of, trying out the 0, 3 squared, cube root of 9. Also negative or positive, so still a negative. So we are decreasing on that interval as well. So this function is decreasing on negative infinity to infinity. So we have our vertical tangent line, so it is still decreasing at that point. If we had a horizontal tangent line, we would not say that it's still decreasing there. Vertical, it is still decreasing. And that should fit with what you know about the basic cube root function. All right. So I'll have you all try one out, then we'll do one together. So let's see if you can analyze the graph using the first derivative for f of x is 1 plus x to the 1/3 power. So go ahead and pause it, try it out, and then we'll go through it together. Okay, welcome back. So f prime of x, 1/3 by 1 plus x to the negative 2/3 times 1, so our chain rule. And just to make it a little bit easier to evaluate, we can write it with positive exponents, either to the positive 2/3 or with the cube root involved. All right, so there's nowhere that this is going to equal 0. All variables are in the denominator. Set it equal to 0. Variables clear out. So we have no horizontal tangent line. We do have a vertical tangent line at x is negative 1. So then we just test points on either side of negative 1, so maybe x is negative 5 and x is 0. So f prime of negative 5, we have a positive 1 over 3 times the cube root of negative 4 squared is positive 16. Positive over positive is a positive. F prime of 0, 1 over 3 times the cube root of 1, which is positive 1/3. All we care about is the positive part. So this one is increasing. Negative infinity, infinity. This is always increasing. All right. So next up, we'll look at something that has a discontinuity. So we'll look at f of x is reciprocal of the sum of x and 5. So I'll take one moment to rewrite that in an easier to differentiate format. So then f prime of x, -1 times hang on to your x plus 5, take 1 off of the exponent, multiply by the derivative of the argument. So f prime of x, -1 over x plus 5 quantity squared. So no horizontal tangent line. If I set this thing to 0 and clear the fraction, I get 0 equals -1, so no horizontal tangent line. So then we have a vertical tangent line. At x is -5. So then we're looking at places where this is increasing, decreasing, or constant. So again, quick little number line, pick a guinea pig on either side. So f prime of -6 is -1 over -1 squared is 1, so that's a negative. F prime of 0, -1 over 25, also negative. This one, however, I cannot say that this is decreasing on -infinity, infinity. The main difference is that in the original function, we're still not defined at -5. All the other functions, we were still defined in the original one at the critical value. This one is undefined at -5. So there's a gap in the graph. So if it's undefined there, it can't be increasing or decreasing there. So this one is decreasing -infinity, -5, union, -5, infinity. So I can't just say -infinity to infinity because the function doesn't exist at -5. All right. So next up, we look at local extrema. And the first derivative test. So we'll set the scene, let f be continuous on some open interval a, b, and c is on the open interval a, b. If f prime of c is equal to 0 or f prime of c does not exist, then c, x equals c, may be the local max, local min. Could be a local maximum, could be a local minimum. We're not guaranteed, we just say it may be. So the idea is we do want to know what's going on with the first derivative. So we find the critical number c, and if we see that the function is increasing on one side of c, decreasing on the other side of c, then c is a local max. Similarly, if we flip that over, C would be a local min. There are times where it's increasing, pauses, and increases again. Then it's neither a local max nor a local min. Alright, so let's play with one where we run the first derivative test looking for local extrema. So f of x for this one will be 2x cubed plus 6x squared minus 90x plus 1. Local is sometimes also referred to as relative. Both are referring to the same thing, the highest or lowest point in some small neighborhood around a point. So f prime of x, 6x squared plus 12x minus 90. We'll set that thing to 0. And we can go ahead and factor a 6 as well. So 0 is 6 by, let's say, x plus 5 by x minus 3. So x is negative 5, or x is positive 3. That is an ugly 5. Those are my critical values. So all that means is my number line now has three places to test 3 intervals instead of the 2 intervals we'd been working with before, but otherwise same ideas. So we'll test out maybe x equals negative 10, x is 0, and x is 10. So f prime of negative 10. So let's see. Now we'll go with the factored version just to make the sign number work a little bit easier. So 6 is always a positive. Negative 10 plus 5 is a negative. Negative 10 minus 3 is a negative. So that is a positive. So we are increasing on that interval. F prime of 0, positive, times a positive times 0 minus 3 is negative. So negative, so we are decreasing on this interval. And finally, f prime of 10, positive, times a positive times a positive is positive. We're back to increasing. So to find the actual locations, the ordered pairs, we would just plug those into the original. So f of negative 5, plug and chug there. And let's see, that ends up at 351. F of positive 3 ends up is negative 161. So negative 5, positive 351, that ordered pair, since we are increasing on the left side, decreasing on the right side, that is a local max. Our other point, the 3, negative 161, on the left side we were dropping, right side we're going up, that's a local minimum. Also sometimes called the relative minimum. If there were more than one, it would be local minima. More than one, max, local maxima. Just one, maximum and minimum. All right. So on that one, they may also ask us to analyze the graph if they want to know increasing, decreasing, and constant. These are ordered pairs. Intervals are x values, though. So f is increasing on 2 intervals, negative infinity, negative 5, union that up with 3 to infinity. F is decreasing on negative 5, 3. So again, these are not ordered pairs. These 3 are just intervals. Local max, local min are ordered pairs. Okay, so that should be enough for you to do the first section of chapter 4. So if you're in the new book, let's see, so we have 9 to 26 all, and 27 to 55 odd. If you're in the old book, 9 to 26 all, 27 to 45 odd, and 53 to 59. Okay, if you have any questions, please get in touch with me. Otherwise, I hope to see you all soon. Stay safe out there.